Okay, thanks for attending this session, and I hope you can enjoy the rest of the 30 minutes for this very important topic. It's around I think after the large models trend, embodied AI, it will become the very, very important trend to drive all the system infrastructure requirement, especially the system software requirement. So in this talk, you will hear the embodied AI, how we enable that on top of the PyTorch, and also very, very important is how we handle the issue when we need to cross different hardware architecture, different AI chipset architecture. Okay, I came from BAAI, Beijing Academy of Artificial Intelligence. It is the neutral, non-profit research institute, have 6 or 7 years research cover the large model trend, and now have a lot of large model efforts going into the embodied AI. So here, when we talk about the embodied AI, actually for the robot end-to-end, usually current stage, we still will break it into two models. One is like the human's brain. Usually, our human's brain it will be responsible for the thinking, language, learning, reasoning, those kind of high-level things. And we also have the human's cerebellum, that is for the action control. That is for the human's action control coordination for different parts of our body. So similar for the human, for the embodied AI, the robot, current stage, we also have the brain model. It will be responsible to understand the physical world, to interact with the human's intention, to do the inference, and to do the planning. For example, if we give it a complex task to clean up this room, then it is the human's robot, the robot's model to do this high-level decision, to do the high-level planning, and divide this planning into the short task. And the robot's cerebellum model, usually it is the VLA model. VLA model means the vision, language, action model. It will get the high-level task and break it into the short the instruction, and then the output the action. Okay. And usually, current stage, the robot brain, it is the VLM model, visual language, this multimodal model, and it can be deployed in the cloud. And for the VLA, that cerebellum model, and usually we want to deploy it in the edge together with the hardware of the robot. And for this model, again, we will have the data processing, training, and evaluation. So very similar to our large model part. Okay, and in the past more than 2 years, actually, our lab, we have the very deep research in this area. And this year, we released the 2 models. One is the VLM model, that is the brain model. It has been released in twice the 2.0 version now. And the other one, VLA model, it is the RoboBrain X0, and we just released it last month. Okay. So since we got a lot of experience for these 2 models, we trained it from the scratch to do the post-training for these 2 models, and also the deployment inference for these 2 models. So today, the rest of this talk is based on these 2 models' experience and based on our system software's view. Okay, usually, let's see how is the brain model and VLA model today. Again, the brain model, it will the input usually is the human's language instruction, and also the structure, the scenario data. And also, we will input it with the image or video, those kind of visual part, and do the encoder for that. And the output of this model, usually it is to do the reasoning output, planning for task, is again the text output. On the other part, it is the VLA model. That's a smaller model, usually smaller model. And usually the structure is the VLM plus the action expert. okay? And the input for this model actually is the multimodal input. It will include the instruction input, video input, and also the state input from the hardware. The state input from hardware, like the joints and the effectors for the hardware on the robot, and those it is the very structured input data. And the output, it will be the action. The action, usually it is the absolute state or the movement of the joints of the hardware and the effectors at different time slot, okay? And the current stage VLM model, like for example, the RoboBrain 2.0 belong to the VLM model. And the VLA model put onto the robot, it is like the Pi0 or GR3, that's from ByteDance. And BAAI will also just release the X0 model that is belong to the VLA model, okay. So these are two different models. And if we look at the whole embodied AI from the upstream to the downstream, we can see a lot of different steps, all include a lot of computation requirement. Start from the data collection. After the data collection, we need to do a lot of data filtering, data annotation, and we also will do a lot of simulation, right? This morning, NVIDIA's leader introduced the simulation work, Omniverse, those kind of things. So all related to the compute. And model training, of course, it includes the brain model and VLA model, these two models, pre-training and post-training for these two models. And after the training with this two generic model, then we usually will do the simulation and alignments. The alignments, for example, we will do the reinforcement learning. And after those kinds of post-training, no matter the reinforcement learning or SFT, then we can deploy the model inference. And this deployment can be on the cloud or on the edge. And we also will have the action control. That's very low-level action control near the real-time control on the hardware. And the final step, usually we need to do the evaluation. And this evaluation, usually we want it to be evaluated with the real hardware, okay? And here, since we talk about the models, and among these different stages, especially for the model training, reinforcement learning, alignment, model inference, and the evaluation on the real hardware, we also need to do the inference, right? So all this will relate very, very related to the computation with the PyTorch. And here I summarized this computation with very important three key requirements. The first one is it will very need the cross-chip support. That means that no matter the training or inference, very happen we need to do the training on one kind of chipset, then the inference is deployed on the other chipset. So that's called the cross-chip support. The second thing is we need to do the delayed control. And the last one is trust and safe computing. Very important, since the robot, it will very close to our real life, very close to it will happen all the action in the physical world. So how to ensure the trust and safe computing to ensure the environment will be safe, that's very important. But today, I will focus on the first two parts. First is how to enable the cross-chip architecture support. And that's the very key part is cross-chip support today in our solution is based on the FlagOS, this very open source unified system software for different AI chipsets. And first, I want to share why we see that embodied AI today, we will need more support for the cross-chip architecture. Because we see that in the edge, close to the edge side, we can see there will be more diversity for the chipset architecture. So today we will see that a lot of current robot hardware, it will run with the NVIDIA Orin. And we also will already see that there's other chip provider who has already the inference chipsets in the data center side. Now they are preparing the downsizing chipset solution. and they want to put their chipset in the robots as well. So we can foresee that there will be more and more hardware options on the edge for the robot. And the second one is, very happen, we will train the model on the cloud with the AMD or with Huawei's chipset or with others' chipset, but deploy at the edge on NVIDIA's chipset. So this very happen, I already can see a lot of different examples and competition have this kinds of scenario. So how can we do that, right? Cross-chain on one kind of chipset, but deploy on the other chipset. And the other thing is, still, so today we have already have a lot of different kinds of AI chipsets in industry, but still have a huge gap between the human's brain and AI chips. If you take this view, human brain, no matter the brain computation, memory, we actually have a much larger volume than that on the single chipset. So if we really want to put this high intelligence in the single chipset put into the robot, today, compared with the human's brain, we actually, human's brain, we can use much less power and much less data to achieve high intelligence level. So that means that we still need the innovation and breakthrough in hardware, okay? But what is today's barrier? Today's barrier is we currently different AI chipsets have their own different hardware architecture, different instruction, different compiler, and even different version of operator libraries. So it makes our user very difficult to migrate their code from one chipset to the other chipset. So the problem is very fragmented software ecosystem. So here is FlagOS. FlagOS is co-developed by including the BAAI team, co-developed by close to 20 teams from global, and it's already become the widest range support for AI chipset in the world. And actually, it currently well supported the PyTorch and cover the support on different AI chipsets, including it supports NVIDIA, AMD, NPU from Huawei, GPU, these kinds of very GPU-like chipsets, and those special designed hardware. And it also can support the RISC-V AI chipset and ARM NPU, okay. And it includes a very key part, include 4 very important open source libraries, AI operator libraries, FlagGEMs, Unified AI Compiler, Parallel Framework, FlagScale, and the Unified Communication Libraries. Okay, it already supports different kinds of large model, LLM, multimodal model, and the embodied AI we talked today. And it also can support the environment run in data center and the edge. So based on this, actually that's how we can do the cross-platform support for the embodied AI. And a little bit detail, the first is, since our embodied AI, no matter the VLM model or VLA model, it will need a lot of operator kernels to support our algorithm. So the first thing is the FlagGEMs in FlagOS, that is already become the largest Triton operator library. And we already have more than 200 operators support a lot of different models. And it has been included in PyTorch ecosystem project. And it's written in Triton language, okay? And with this Triton operator library, we also compare the performance with that on NVIDIA. And we found that most of the operators written in Triton in this library already can beat the performance of CUDA on the same NVIDIA hardware. So first thing is we need to prepare enough operator kernels and also in the good performance, okay? And here we list those models we supported, and you can see that I highlight in the green color are those models, either is the VLM model or the embodied AI robot model. The second thing, very important to support this cross-platform, it is the AI compiler. And this morning, just now, you might heard about the PyTorch compiler team to talk about the compiler, how important of compiler in PyTorch. And yes, for the Triton, since we use the Triton language, which is very open source language to implement the operators, and we also developed the enhanced compiler for Triton language. We call it the FlagTree. It today already supports a lot of different kinds of hardware, AI chipset. Again, we support the NVIDIA NPU from Huawei and also other chipsets. And the very important thing is we extended its language to support the hints to represent the hardware feature so that this Triton, this FlagTree compiler can get even better performance than the original Triton. And we also did a lot of optimization in the runtime. So again, it can provide us better performance. So here, just the very important result is for the Q1, this model, we 100% replace the Triton implementation with replace the CUDA implementation with this Triton library. And we changed the underline the compiler into the FlagTree and get a very good performance. Okay, already very close to the best performance in CUDA. So it gives us the confidence. We have the poster actually in the downstairs in the exhibition hall. You can look at that. Okay. And the third one is actually the FlagScale. It is the framework for the training and the inference. Today, we have the quite different architecture of the models, language model, multimodal model, and this embodied AI models. We have different chipsets, and we have different scale of the clusters. So we cannot rely on the humans experts to do the optimization for the training and inference. So that's why we developed the fully automatic strategy so that for any given this new hardware, and we can use FlagScale to deploy and automatically optimize the parallel strategy and get the best performance. Here you can see that compared with the experts result, we already achieved the 10 to 20% of the advantage compared with the experts. And we also use that for the embodied AI. And the other thing is today, you also might notice that we today have the different framework, parallel framework or acceleration framework for training and inference. Especially for inference, today we have the VLM, SGLang, Llama CPP. Actually, different inference engine will have different advantage. So for our user, again, you will confuse that for a given model, which engine should I choose? VLM, SGLang, or Llama CPP. So FlagScale can support the different chipsets and this backend acceleration engine. It will automatically select the best one configuration with the configuration and give you the best performance for the inference. And this is another very important one. Unify the communication library, since the different chipsets have different communication libraries, so we also developed the unified communication library. Okay, based on all this very core technology with the FlagOS, that's how we can do this migration without a human's effort to do the migration across the different chipsets. The second one is the end-to-end enablement for an optimization. Based on this FlagOS, we can support the training for the brain model, VLM model, and inference it in the cloud. We can train the VLA model in the cloud and deploy the inference at the edge. And we also can support the cloud edge high efficient coordination. Okay, so first is the training the brain model VLM in the cloud. Actually, we can see a lot of challenges to do that if we target for high efficient training. The challenge like in the data loading, because currently PyTorch has a high CPU overhead if we just use its native data loader. Parallelization, if we just use the common tool like a Llama factory, then it cannot support the high performance training for the multimodal model. And also the other one is memory bottleneck. So actually with the FlagOS, especially our framework, the FlagScale, we solved a lot of different kinds of issues, including the data loader, the parallel, and then the result here is with the FlagScale, compared with the default, the Llama factory, we can get more than 2 times speed up for the training. So that's the first thing. The second thing is the inference of this VLM model. And first deployment challenge is the very fragmented hardware ecosystem. But again, since we have the FlagOS, so that's not a problem for us. We can deploy the model trained in chips cluster A and deploy it in another type of hardware. And the other thing is a multi-backend selection, VLM, Edgeline, or Llama CPP. I just now already mentioned that. And also the performance optimization. So here by include all the different stuff from supported by the FlagOS, including the auto-tuning, backend and multi-chip support, and also we will do the hybrid quantization. You will see that with the, for example, the normal the GPU 4090, this very deployed very close to the edge side, we can see there's the performance speed up. Okay, and for the VLA model, since this is the embodied VLA model, the challenge is if you have 2 stages, one is the pre-training and the other one is fine-tuning. So when we want to train the VLA model, but the pre-training is usually is the web data set, and the fine-tuning, usually we will have the robotic, the multimodal data set. These 2 kinds of data is quite different. The web data set actually is normal, the multimodal, the pair of the video and caption, pair of the images and caption. Usually it's these kinds of data. But for the robotic data set, it will include the instruction in text. It will include usually 3 image or 3 video from different cameras, and also it will include the structured data, the JSON data set of the degree of freedom, different hardware location, XYZ location, that kinds of information. So that's the pre-training and fine-tuning. These 2-stage data sets are different. And the training is also different. Pre-training, it will need to train on the whole all parameter. In this case, we use the 3 billion, this size of the parameter backbone. And for the post-training, usually we will freeze the VLM side, and we just will train on the action expert. It will be much smaller, okay. So again, we do a lot of different optimization, leverage the FlagScale, we can achieve the multi-stage data pipeline to handle both the pre-training and the fine-tuning for different kinds of data sets, and have the computation reduction, those kind of things. For the inference on the embodied AI VLM, we found that we cannot only rely on the system levels optimization. We need to work very closely with the algorithm team to do the improvement of the end-to-end performance. And for example, we can see that from OpenVLA to Pi0 or Pi0 fast, there's a couple of different algorithm change. And besides, we also need to very carefully to do the quantization because the time, I will skip this one. And we also will do the high efficient cooperation between cloud and edge model. So our FlagScale also developed a different support to cooperate the cloud side and edge side to support the slave and master, this kind of cooperation. And we also, through the robot skill registration, we also will reduce the tokens so that that's how we can shorten the latency, okay? And here, we also show the framework, how we 5 steps very easily to run up the things. And currently, it supports different kinds of embodied AI models, including Pi0, robotic, and RoboBrain different versions. And we also currently is all on site on the FlagScale. You can see that we already support different kinds of model, but particular, I highlight that those is used in the robotic. And we also compare that with Robot. Robot is a very famous framework in Hugging Face, and how is that advantage? Advantage is it support both the training, inference, multi-chip support, one-stop Docker image support, okay, and it supports both the VLM, VLM. So all the required thing for this latest model for the embodied AI currently already be supported by the FlagScale. And here is, you can get more resources. And here is with this FlagOS, we really can run all our demo and do the experiment and evaluation in our lab, okay. And this is the final one is actually based on this, again, on one hand, we need to control the latency. On the other hand, we need to better support the new coming the hardware architecture. So by using the FlagScale, you can see that we can use our AI compiler to support the new if you have a new chipset, we can use our FlagTree AI compiler to support that. If you have the new operator for embodied AI, then we will use the FlagGEMs, this library, to support more and more operator from embodied AI. And for the FlagScale, we support both the inference and high efficiency training for no matter the brain model or the VLA model. And we have another important thing is flat release. Today, users, they don't need to do the migration. If they already have the hardware, they want to use some kinds of embodied AI model, they just go to the flat release on Hugging Face, can directly download that. Okay, and I finished here and see any more question. How large? VLA model. Okay, currently in our lab, we use the around the 3.3 billion that size of the model. And if you look at the current, also have other lab, they also release some new open source model. Is around the 2 billion to 4 billion, usually is this size. So that's why we think this size model is already good to fit into those edge AI chipset. But those AI chipsets need to be able to support around at least 100 TOPS, and with around 20 to 30 gigabyte in memory. Yeah.
Also, what the quantization technique you're using? Quantization technique
it's around 8-bit.
Integer?
Yeah, right. Any more questions? Sorry, FlagTree. Triton language? Okay, yeah. Actually, FlagTree, yeah, this is our AI compiler. It is the enhanced compiler compared with Triton's original compiler. So if you have the Triton language, you have the code written in Triton, you can use the OpenAI's, the original version of the Triton compiler, or you can use FlagTree. So it's fully compatible. But with the FlagTree library compiler, we can allow you to support more backend. Yeah, because today's OpenAI's Triton compiler, they mainly support NVIDIA AMD. But for us, because we need to support more chipset, so we use the FlagTree, we developed the FlagTree for the ecosystem. Any more questions? Okay, if not, then we can have more discussion. If you have the interest, just try on the link and you can find the resource. Thanks all.